Because in classical probabilities, everything is hypothetical. Everything is just imagine this situation and then try to figure it out, much like a brain teaser or something. It helps a lot to have a couple graphical organizers for how to think about the problem. So one of those organizers is called a tree diagram. So it helps us kind of keep straight what's happening. Now, you can only really use it effectively for some pretty small data sets because, or excuse me, probability outcome sets because, you get 52 outcomes and it just becomes a nightmare to draw. But nevertheless, for beginning problems, it kind of helps us out. So this is an example over here on the right of a very simple tree diagram. It's a tree diagram for a single coin toss. So you start here at the beginning, and then time goes from left to right on the diagram. So here's the start, and then time passes this way to the right. And you have two outcomes. So you have a branch that goes this way, and outcome heads, and branch this way, outcome tails. Right? Two branches, two outcomes. All right, so let's imagine you are going to have two children in the future. What would be their genders? So assume only male and female. Again, we don't want to get into just because it makes everything so complicated, and we're going to assume everything's equally likely. Okay, I know there are people that can be born with both male and female characteristics. I'm not, it happens in 1 out of every 10,000 births or so. But again, for our purposes, I'm just trying to make a simple tree diagram. All right, so let me pause you, and I'm going to go draw this, and I'll be right back. There we go. I think I got it. So, all right, here's the first child. So ignore these ones over here. Matter of fact, I'm going to color these. So the first child is going to be green arrows. Oh, those are too light. Hold on 1 second. There we go. That's a little bit easier to see. Okay, so the green arrow is the first child. So you have your first child, right? And it's either male or female. Okay, and then you have your second child, and that's the blue arrow. So this branch up here is, hey, I had a male for my first child, then I could have a second child that's male, or I could have a second child that's female. Or I could go female first child, and then I could have a second child that's male, or a second child that's female. And then you want to make sure you list out your sample space over here. Male, 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 female, female, male, female, female. All right. What is the assumed probability of each outcome? Well, that would be 1 out of 4, which is 0.25. Now, why do I say that? Well, because we assume, hold on, because we assumed that male and female, if I could spell it, were equally likely, i.e. 50-50, right? 50-50 shot, 50% chance, right? So therefore, which I suppose is redundant, so all 4 of the possible outcomes are subsequently equally likely. In other words, you assume male and female was equally likely, therefore all 4 of these outcomes, there's 4 of them, so every one of them's got a 1 in 4 shot. All right, define the event having exactly 1 boy. Well, there's 2 that satisfy having exactly 1 boy. You could have male-female, or you could have female-male. Both of those have exactly 1 boy. All right, is that a simple event? No, there are 2 outcomes in the event, not just 1. Right? Simple events have to be just 1 outcome. So if I said having exactly 2 boys, that would have been a simple event because male-male is the only way that can happen. All right, so let's find the probability of F. Well, yet again, it's 2 out of the 4 possibilities, which is 1/2, which is 0.5. Oopsie, shouldn't have pressed that. 0.5, which is 50%. All of those work. Okay. All right, so now you're kind of getting, hopefully, the idea of some of these probabilities. So we have to have some rules for probabilities that are showing up in the problems that we're doing. Now the first rule is that every probability has to be between, and I'll write it out in words. Every probability, why is that Times New Roman? I don't know. Hold on. There we go. All right, every probability is between 0 and 1, inclusive. Okay, that's what this is saying up here. What does that mean? It means the lowest a probability can be is 0. The highest is 1. No negative probabilities are possible. You can never, ever, ever have a negative probability. You can never have a probability bigger than 1. Okay. Then the next one says the sum of all the probabilities in a sample space must equal, well, I should say the sum of all the probabilities of the outcomes, not the events, because events can be bigger than 1. Of all the outcomes in a sample space equals 1, 100%. Because you have to have everything accounted for by the time it's all over. So for example, if you look back to, there we go. If you look back to these probabilities, if this is a fourth and this is a fourth, a fourth, a fourth, then all 4 of them add up to 1 because you have all things accounted for, right? All right, so that's what that second one says. Now, if a probability, excuse me, if an event is impossible, then its probability is equal to 0. We saw that already with the red spade thing, right? If something's impossible, then there's a no chance it's going to happen, right? No chance makes 0 probability. All right, what if it's for sure going to happen? Then its probability is 1 or 100%, right? It has to happen because it's certain. No question about it, this will happen. That's a 100% chance. Okay? An unusual event would be probably a probability of occurring that's very low, right? Small chance of it happening. Now for our book, we're going to say less than 0.05, which is 5%. Now that shouldn't come as any great shock to you all because in chapter 3, remember chapter 3? We said that things were unusual if they were less than 5%. That's why more than 2, remember, more than 2 standard deviations away. Why? Well, because on a normal curve, the tails of a normal distribution are worth 5%. Right? So anything that's less than 5% chance is considered unusual for our purposes. And again, we've already run into that. It was in section 3.2. It was one of the last things we covered. When we covered the empirical rule, we mentioned this. All right. Now, a probability model we're going to work with a lot. It's a list, usually in table form, but it doesn't have to be. But for our purposes, it often will be. So it's a list of all the possible outcomes of a probability experiment and each outcome's probability. Now, there are other ones that are continuous. I'm talking about really discrete things here. Remember discrete and continuous from chapter 1, right? Discrete means there are single value outcomes. We'll talk about continuous curves like the empirical curve, the normal curve, later on in chapter 7. Okay, so I want you also to notice that sometimes you can have the same experiment, but you can have more than one probability model depending on what you were interested in. So, for example, I have 2 probability models here, and they're both for what we just did right here with the male, female, male, male, that thing. Okay, so I want you to see that both of them are completely valid. Why? Well, because the one on the left, and you know what, I think I'm going to put it in table form. Hold on one second. Hold on. Okay, here we go. So this one over here considers each individual outcome, right? And it's looking at the genders of every single child, right? So considers each individual outcome, the genders of the individual children, right? So you can see male, 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 female, and so on. This probability model is based off the same tree diagram, but I only care about the number of girls. So what that's going to mean is the male, female, and female, male get kind of lumped together in the middle there. So these 2 right here get, and I'll even highlight them for you so you can see it. These 2 right here get turned into that one right there. And then male, male is right here. I'll make it orange. That's right there, because if you have male, male, you have 0 girls, right? And then if you have female, female, I'll make that one red for the fun of it. And then there we go, that's them. Okay, so it's the same diagram. It's the same tree diagram that's the foundation for what we're doing, but you can write them based on the number of girls or the genders of the particular children, and they're both completely correct. So you have to pay attention to what was asked for in the problem. All right, so let's look at some probability models, or are they? So I want to know, are these valid probability models or not? So let me, again, add a little bit down here for me to write in. So if you want to check whether they're valid probability models, you have to check them against the rules that we have, which, by the way, both of these satisfied those rules. These added up to 1, right? These add up to 1. And what else? Every probability is between 0 and 1. There's no negative probabilities. There's no probabilities larger than 1. Okay, so if you look at this one over here, this is a valid probability model. I'm going to center that. It's driving me nuts. There we go. Probability model, because the probabilities are all between 0 and 1, and they add up to 100% total. Okay? This one is not a valid probability, not a valid probability model. And the reason being, it's because if you add them up, this is 0.7, 0.8, 1.2. Oh no, 1.1, sorry. So the probabilities sum to 1.1, but they should have summed to 1, 0. There we go. Okay, I want to stop right there because the next stuff is going to take a little bit of work. So we'll pause here, and I'll meet you back here for the next batch, which is even more tree diagrams and the multiplication rule of counting. All right, see you then.